Hello, everybody, and welcome to today's presentation, Creating a Killer Database Architecture with Kubernetes and MariaDB, brought to you by MariaDB. I'd like to introduce you to our presenter, Thomas Boyd. Thomas joined MariaDB in 2017. He brings 25 years of experience in the IT industry with a strategic focus on databases and data storage technologies. Prior to MariaDB, Thomas worked at Oracle, Hewlett-Packard, MongoDB, as well as with smaller startups, and as an independent consultant in the San Francisco Bay Area.
Fantastic, and thank you for that introduction. Welcome everyone, and thank you for spending some time with me today. We're going to talk about containers and Kubernetes and MariaDB, and our agenda is relatively straightforward. I like to assume that there are some people in the audience who are relatively new to the containers and Kubernetes world. So we're going to spend the first half of the presentation with a quick rundown of those technologies, and then we'll dive into the real meat of the presentation and talk about what MariaDB has been doing in this space. So containers. Essentially what containers are is a mechanism for bundling together all of the code and dependencies required for getting your piece or a piece of software to run, and to run in the same fashion no matter which environment you're running it in. So what you're looking at here is a picture that shows, the runtime portion of the code. So things like, a Java runtime, or if you're running in Python, the Python interpreter, making sure that you have the right version of Python installed. Those of you who have been doing development over the last 10 plus years know that a lot of the code we write really relies on libraries that are available from other developers. And so the image that you're creating, the bundle of software that you're creating, needs to have all of these libraries installed as well. These could be operating system libraries or runtime specific libraries. And then the code itself, the actual Python code or Java code that you're putting together to run your application. And in this case, I say application, we're really talking about databases, but from the container perspective, the database is just another application. So you create a definition of all the pieces that are required to run that. That gets moved into a static file called an image. And that image then becomes the boilerplate that's going to be passed around and executed by the various servers that are going to be executing that container. So an image is a static file. A container is an instantiation of that image up and running of the code executing. And so this is the core of what containers are. And they really bring three main benefits to the IT world. And the first is that encapsulation of dependencies. The idea that I no longer, as I'm going to be running my code in my test environment and then my staging environment and then my production environment, I no longer have to worry about whether those environments have been properly prepared to run that code such that it will get the same behavior. By having the operating system defined, the operating system level, the patches, the execution environment, that runtime that I talked about, by having all of those bundled together, it means that we can run these same images instantiated as containers in our dev environment, our test environment, our staging and production environments, and know that we're going to get the same behavior. And that's really a big win. I mean, those of us who've been around for a long time are, used to the systems administration tasks and the hassles that happen as you get slightly different behaviors as you move to those different environments. One other thing you get from it is process isolation. So these containers, as you saw in that previous picture, can be running as multiple containers on the same physical host. And you do have the ability to fence off certain amounts of memory and CPU. To a lesser extent, there may be some controls around storage I/O and network consumption of network bandwidth. And this allows you to have this strong isolation, which is also important to knowing that you're going to have the same kinds of performance characteristics that you expect as you're isolating these containers on different hosts. In some ways, you can think of containers really as faster, lighter weight virtualization. And I think the container purists would say that there's a lot more to containers than that, and that's true. But in a lot of ways, the fast and lightweight nature of containers is what's really caused them to take off and has allowed them to supplant in many places a lot of the investments that were made in virtual machines. And really, there's, the underlying reason for this is that containers themselves, unlike on the left-hand side of this picture here, where you see a virtualized environment, containers don't have that guest operating system. So they're basically not having to take the large footprint, storage footprint. So the image files themselves are much, much smaller than a virtual machine image, for example. So that makes it easier for them to be passed around and instantiated on different servers, or indeed easier for a software vendor like MariaDB to provide a container image that just simply is not as large as or as complex as providing a virtual machine image. In addition to that size issue, the startup time of containers is much, much faster. So as where virtual machines, and oftentimes in a best case environment, you were talking about multiple seconds to start up a new virtual machine, containers, when they're spinning up, depending on how complex they are and whether there's some complex initialization logic, can be on the order of tens of milliseconds or maybe hundreds of milliseconds to spin up. And that difference is a real game changer. Now containers can be used to provide elasticity to your applications. So if you need to spin up more web servers or more application servers as your load increases, you can have the next 10 or the next 100 web servers spinning up on the order of a few hundreds of milliseconds. So you can really be very reactive or proactive, I should say, about spinning up, and scaling down those environments. So this has really been a big win for lots of IT organizations, and you have seen containers become very, very popular in stateless applications. So again, things like proxies, web servers, to a certain degree application servers as well, where there's no state that's being saved, and you can take advantage of this elastic spin up and spin down of infrastructure. Again, for those of you who are new to containers, this is an example of how an image is defined. And what we're looking at here is what's called a Docker file. I'll talk a little bit about the relationship between Docker and containers. But if we read this from the top down, the very first thing that we're declaring here is that this image file is going to be based on another image file that's defined by CentOS. So we're basically taking a base CentOS 7 image, and then we're layering in the other pieces of code, the other pieces of libraries, and our application code that we want on top of that. So that's where you see, for example, we're copying in a configuration file for the MariaDB database. That's that copy line. We're also creating some directories that are going to be required for properly running MariaDB. You can also see us using the package installer to make sure that we have the latest up-to-date packages for the CentOS operating system, and we're installing a host name package and some user definitions, et cetera, et cetera. I don't mean to go into a lot of detail here. You do see a line where we're talking about attaching an external host volume. And I am going to talk later about storage. Containers do run isolated. Of course, a completely isolated piece of software is of no use to anybody, so you need to expose a port that the outside world can use to speak to your container. And then very last in there, you see the entry point line, which defines the script that's going to be executed when the container instantiates itself. So oftentimes you'll see, especially with complex software, a relatively complex entry point script. So this is a script that lived in this directory that becomes part of the image file that's getting built that will handle some of the complex startup steps to get the MariaDB server up and running. So what happens is this Docker file is defined. You run a Docker command called Docker build that translates this file into that static image, and then that image itself is passed around to become the running container on the server when it's instantiated as running software. Probably not new to some people, but critical to some foundational understanding of containers. I do like to spend a little time mentioning this relationship between Docker and containers. And the most important thing to understand here is, for all intents and purposes, the image files, well, really the Docker file we just saw that gets translated to an image that is then executed inside a Docker runtime image, those have been standardized. And there's a company called Docker that was really at the forefront of popularizing containers. And they had donated or have donated those definitions to the Open Container Initiative. So there's a third-party foundation now that's managing those definitions. And for all intents and purposes, anybody who's running containers these days is running Docker containers, right? So they're using that Docker file we saw. It's a Docker image, and it's running in some version of a Docker image. And the rules about how those images are executed are well-defined and understood. Docker, the company, does have a number of other things that surround containers and help with orchestration and management. And that's really what you're seeing here with the Docker machine and Docker Swarm and Docker Compose are higher level mechanisms for helping lay down Docker images or for orchestrating multiple containers that are running together as part of your application stack. That picture or that space of orchestration and management has changed quite a bit over the last even over the last year. It's changed a fair amount, and it's where Kubernetes comes into play. So we're going to spend some time talking about that. I just didn't want you to be confused about the various components and what has Docker in the name and what doesn't. So Kubernetes. Easiest way to explain this is that once you have a large number of containers that are running in your environment, and again, we may be talking development environments, test environments, relatively complex application stacks, you have this second level problem of, well, how do I manage and orchestrate and monitor all of these containers that are running? And what happens when when a node goes down, a physical machine goes down that was hosting some of my containers? How do those get reinstantiated on another physical node? And even before containers really burst on the scene, there were companies that were doing this kind of work, either around virtual machines or using other mechanisms for managing software. These were companies like Mesosphere, Red Hat's OpenShift project, and they in fact had their own management mechanisms for containers. But what happened is there was a project inside Google, which was a large user of containers, called Kubernetes, which was a separate project in exactly this space for container, explicitly to container management and orchestration and monitoring of those containers. Over the last couple of years, that has really taken off as a de facto standard for the mechanism for managing containers. So much so that companies like Mesosphere and the Red Hat OpenShift project have adopted the core Kubernetes mechanisms inside their management platforms as the way that they're going to manage containers going forward. And what we're ending up with here is really a nice, widely adopted standard, both in terms of the Docker files and containers and runtime environments, and now the orchestration environments for defining these more complex application stacks, which is a big win for a company like MariaDB. So we don't have to spend a lot of time figuring out how we're going to integrate into disparate kinds of orchestration environments or even disparate container definitions. Unlike in the virtual machine world, where there are several different definitions of hypervisors for running virtual machines and several different mechanisms for managing the higher level stacks for orchestrations of virtual machines. So we're now in a position where we can provide container files or image files that define the MariaDB software and some Kubernetes components on top of that that can help you set up these relatively complex topologies of MariaDB. Likewise, in the public cloud space, whether it's Google, Amazon, Azure, Alibaba, all of the big public cloud players now not only have environments for hosting and running containers, but they have hosted versions of Kubernetes to help you orchestrate these complex topologies. And Google, of course, was the first mover there. Amazon actually had their own container management environments, a lot like OpenShift and Mesosphere did, but they now also have a hosted Kubernetes environment. So really widespread mechanism such that we can begin to guarantee that you have the same experience with the MariaDB database no matter where you're running it. It's the same image files, it's the same Kubernetes operator. And this is really, where the subtitle of this presentation comes in, this idea that we can have a really killer application that's hybrid in that it can run in your own data center on your own Kubernetes or OpenShift deployment, or in the public cloud, and you'll have the same, the same performance characteristics and the same management plane that you're using to monitor and make changes to your MariaDB clusters. And it's a real chance to break the vendor lock-in that some of the big cloud vendors are getting at this point, where once you've invested a whole lot of time in managing your databases through one of the database as a service offerings that's only available on Amazon or only available on Google, you're really locked in there, and your chance to take advantage of other clouds and reuse your expertise in other environments is quite limited. And we're really happy to see this chance to move towards a more standards-based approach to managing this infrastructure. And I think everybody loves Amazon and Google and Azure, and I think they're excellent infrastructure providers. The kinds of machines that you can get to run on are excellent. And I think the cost of ownership issue and the setup issues, that the setup efficiencies that they provide are great. But now we have an ability to really layer on that database expertise on top of that infrastructure and provide a world-class database service that's portable across those locations. This slide lays out some of the Kubernetes components. And I think the first thing to understand is, reading from the right-hand side, that it is all about the physical nodes that are going to be running your software. And those physical nodes are going to have individual containers instantiated on them, and they're going to have perhaps host volumes that those containers are writing durable data to. In order for that to happen in a Kubernetes environment, the Kubernetes environment has made sure that there's a Docker runtime that exists on those individual physical nodes. And there's essentially an API service layer called a kubelet, which allows that node to take instructions from the Kubernetes master. So the Kubernetes master is where all these definitions of your software, my 3-node replica set, my stateful set that has 5 nodes in it, my proxy server that has 100 different versions that I want up and running, and a service that routes my calls across those 100 different proxy servers. All of those things are defined in the Kubernetes master, and the Kubernetes master's job is to watch those definitions and make sure that it has instantiated the correct elements down on those nodes. For the operators, we interact with those Kubernetes masters and define those items, those replica sets and jobs and deployments through either a REST API that's available, through a command line tool called kubectl, or through a UI. And the base Kubernetes UI has a little dashboard that you see a screenshot of there. And this at a high level is how Kubernetes works. I guess maybe the one thing I didn't mention is obviously the Kubernetes master, those definitions need to have redundancy built in. So you can have multiples of those up and running to make sure that you can't lose your definition of your software that's supposed to be up and running. A deeper look at in the blue here, what you're looking at are the objects that would be defined inside those Kubernetes masters. And the main object that I like to focus on is what's called the controllers. And these are those things like those replica set definitions, stateful set definitions. There are one-time job definitions and a few others of them. But this is where you make that declarative statement of what you want your software to look like, how many instantiations of it you want up and running. Maybe you have some special rules about, I don't want any version of my proxy server to be running on the same physical host, so you can define some rules about how and where those instantiated containers get deployed. And there's this control loop inside the master that watches those controllers and makes sure that it's laying down the correct thing on your actual servers. On the right-hand side here, you're seeing in the black, you're seeing the actual servers where there is an intermediate level definition called a pod, which you can think of as potentially a collection of multiple containers inside an intermediate layer. if that's new to you, you can kind of ignore pods and just think of those controllers laying down your individual containers and volumes. Also, for many of the pieces of software you're defining, you will have a simple Kubernetes level service that the outside world talks to, and that service is responsible for providing the access into those individual containers. And in fact, for things like proxy servers or web servers or application servers, those services themselves, as a Kubernetes definition, can allow you to do round robin access into the underlying pods. We'll talk a little bit about the service layers inside MariaDB. There is a routing service called Maxscale, which has some very database specific stuff that's required if you want to enable some special security capabilities or routing capabilities. There is a higher level element inside Kubernetes called deployments, where you can bundle together multiple controllers and essentially have this definition of your full application stack that you're laying down. And that is a kind of again, a higher level mechanism for bundling together multiple controllers. Okay, so let's talk about MariaDB and what's happening with MariaDB in this space. And before we go there were a couple things that I wanted to cover. And the first really is that historically, containers and Kubernetes have had some real challenges for databases and stateful applications. And the first of them is really around storage. And one of the great strengths of containers and Kubernetes is this idea that, I can scale up and scale down. I can leverage the portability and the mobility of containers for high availability purposes. If one of these nodes goes down, my master can be watching and it says, wow, I just lost a node that was hosting these containers. I'll just start up those containers somewhere else and we'll be off and running. And I'll route all the incoming calls through the service layer to these new containers I've started up, and this is great. And that works fantastic for, again, those stateless applications. But what about a database who still needs access to the underlying storage, to the data? Or what about a database that, can't afford to have poor performance? It really needs low latency access to its data and high throughput. And so there's a whole separate ecosystem now around providing really enterprise class database storage that's persistent on container failure, that is helping enable databases running on containers. There has always been the ability to attach a local volume, a host volume, but then you lose a lot of that portability that you like out of containers. You're going to have to figure out a way, when you've lost that whole node and the associated host volume, you're going to have to figure out a way to create a copy of that data somewhere else when you start it up. The other issue with databases is the containers inside a database stack or inside a database topology can be different. They're heterogeneous. They're performing different roles. And again, I would contrast this with a web server, where every version of the web server that's up and running looks and behaves exactly like every other version of the web server that's up and running. That's really not true when you have MariaDB up and running in a master-slave setup, and one of the nodes is meant to receive all the writes, and the other nodes are there for high availability purposes and for some read scaling purposes. So there's some special tricks that need to be done to manage that kind of situation where the nodes or the containers that are running are fulfilling different roles. The same with the Maxscale router, that advanced proxy that I mentioned, that is yet another kind of node that's running to maintain this database. And lastly, I would say, and this is maybe a little bit of a subpoint of storage, but databases have always had this assumption that up front you're doing a fair amount of planning in terms of the resources that you require. And storage we already talked about, but it also applies to memory and network and CPUs. And part of this again is because it's somewhat difficult to scale up and scale down horizontally without a little bit of planning. You can do it, and certain workloads work well for scaling across multiple nodes. And there are technologies inside MariaDB, like the Spider storage engine, for partitioning data across multiple nodes. But there's a little bit of planning that's required for doing that. And indeed, a little bit of cost as you do those kinds of scale up and scale down operations. So even in the container world, especially for production loads, we do see a fair amount of planning going into what kinds of nodes do I want to run on, how much memory and CPU and storage am I reserving for this, and some advanced planning of, well, I think about 2 years from now, I'm going to need to make sure that I have a landing place for these relatively resource intensive containers as we've added more data or added more users. So I don't think that containers get you completely out of that need for planning. The fully seamless and frictionless elastic scaling up and scaling down, except for a few corner case workloads, isn't really there for databases. Just a brief word on storage and persistence. This, as I mentioned, has changed a lot over the last year. I think that the real takeaway here is that Kubernetes has now standardized on what's called the container storage interface that's allowing third parties now to develop plugins for their specific storage technologies. And so this includes the cloud vendors who are now able to mount, for example, inside Amazon elastic storage volumes into your containers. It includes Diamante, which is a company that we partner with, whose specialty is really setting up Kubernetes in your own data centers. They have an appliance-based approach that has some very high-end appliances, including some silicon level changes that have been done to make storage extremely fast in containerized environments, and still flexible. So the ability to basically have a storage tier that's been defined where you can mount that storage on multiple nodes in your data center play. There are also software-defined storage players like Portworx and Storage OS. And then we have some of the usual suspects around storage vendors like EMC, Dell, and the stuff that Red Hat is doing. So my message here really is that if you're going all in on containers and moving your production environments onto containers, there is some homework to do here in terms of deciding what your storage approach is. I think we've already established that the Docker image files and the Docker runtimes and Kubernetes are really the de facto standards for containers. There's a lot of flexibility and a lot of choice in your storage tier decisions, and they do need to be thought of, particularly for databases. They need to be investigated and chosen carefully. So let's talk about the images that MariaDB has defined and is providing. And again, this is really great for us that we're able to provide images that we know are going to be able to be widely used. The first, maybe before we go there, we're going to talk a little bit about why and when we see people running MariaDB on containers. And the first thing I would say is that by far, maybe 80+% of the environments that we see on containers are being done for dev, test, and demo environments. And for example, for demonstrations, this is something we use widely inside MariaDB for our field organization to be able to go and show complex configurations of MariaDB that are running multiple proxy servers and MariaDB cluster or the master slave setup, and really give a chance for our field to demonstrate and show the capabilities of our software with this really fantastic mechanism for delivering the images and making sure that our field has the same experience, whether it's a brand new sales engineer or a sales engineer that's been with the company for multiple years. And for all those same reasons, it's become very popular for dev and test environments inside IT organizations, inside companies. It's nice to be able to know that your developer who's working right on their laptop can have the same experience as somebody who's working in maybe your more tightly managed test environment. We do see people, obviously using them in production as well. Microservices cases are, maybe one example where it's relatively common, where we have a company that's iterating quickly on their application code and has chosen to deliver that application code through containerized environments. This particular microservice has an associated database with it, and they want to deliver the database also through containers. Some of those databases end up being really more or less static stores. So when you do a rebuild of the database, you start from scratch and there's some kind of a load of data that's associated with that rebuild. Maybe it's even part of the image file. For the more complex microservices that really are managing their own data, then the migration of your changed database image is going to have to include, well, what do I do with the existing data? How does that get upgraded? And so some of the old things that you had to do don't really go away in terms of managing your schema evolution and doing add column calls and those kinds of things and defining new tables. They're just bundled and distributed a different way. We do see companies creating a gold copy of a starter database, for example, that matches their corporate standards. So this might be a case where maybe your company has decided every database, every MariaDB database that's up and running needs to be configured to work with our LDAP environment and use LDAP for database authorization or for database authentication. And this is a great chance for IT organizations to really lay down the standards, but not have to be the bad guys who are telling people to do all this extra work. Instead, providing a copy that's meant to meet their corporate standards. And it's a great way to avoid, getting yourself into the news where it turns out being, it was really a dev or test environment that was improperly configured and allowed a data leak of some kind by having this gold copy that people, no matter where they're working, even on their laptop, are using. And then lastly, I talked about this a little bit before, the fact that containers in Kubernetes are going to be behaving the same on different clouds, whether you're talking the public cloud vendors or your private cloud, allows people to really have this multi-hybrid cloud approach to the way they're managing our databases. And in fact, the MariaDB managed service called SkySQL is built on top of our Kubernetes operator and our container images. And so as we're rolling that service out to the next cloud vendor and the next cloud vendor, we're not having to do a lot of custom work to work in those second and third cloud vendors that we're introducing this service on. So real quickly, I'll just run through a few of the images that are available. The first one is that single server image. So the idea of we're going to get MariaDB server up and running, and it's going to be running in a configuration that's suitable for OLTP workloads. That means underneath the covers, it's using our InnoDB storage engine. Is really as easy as the command that you see right here. Now, this does assume that you've installed a Docker runtime in the environment where you're running this. So, for example, I'm running on Mac OS. I've downloaded the Docker runtime for Mac OS. Once I've done that, I can simply type this command, and there are a few environment variables you can pass in that will change the configuration, set passwords and whatnot, and I have MariaDB up and running on my laptop. Behind the scenes, the way this is working is that the default install of the Docker runtime points to a repository called Docker Hub, where we have staged our images. If you're pointing to Docker Hub, it works just like this. If you were pointing to a corporate repository for images, or if you were running in an OpenShift environment, then you just need to make sure that the correct image is staged into those repositories. All of the documentation for our images are available both on Docker Hub and on GitHub, and those are those two links that you see right there. The last thing I would maybe mention is there are multiple alternative images out there for MariaDB. This is open source software, and some of those images are fine, maybe for test and dev purposes, but this is the route we want you to go if you're looking to move into a production environment, because it allows us to provide support on top of the containers or the MariaDB that's defined and running inside containers. Just a little taste of the variables that you can pass in when you're starting up that container, all sorts of control in terms of creating your new application database and application username and application password, as well as root password and a couple other things. I will also say, if you look into the documentation, there is an initialization script that you can define and pass in that would allow you to do all sorts of bespoke modifications to the startup of this database. This, as I mentioned, MariaDB in containers is wildly popular for development and test purposes, and there are probably countless hundreds of thousands of versions of this up and running right now concurrently as people are working on their laptops and doing either their corporate IT project or their little garage project, a very widely used container. A lot of people may not be aware of MariaDB Column Store, which is MariaDB configured to run for large-scale analytics. So if you're running against terabytes and terabytes of data, doing aggregation and summarization queries that are looking over multiple years of data, maybe it's a sales application and you're summarizing average sales in quarter per rep over the last few years. This version of the database is configured with a different storage engine that stores the data in a columnar format, which allows for orders of magnitude improvement on those kinds of queries. So again, the documentation is available in GitHub and Docker Hub. The command to instantiate it and run it as a single node on your laptop is right there. Again, it's as simple as running that. Because Column Store is often thought of as something that's going to be attacking very large data sets, we do also provide a Docker Compose script that allows you to lay down a multi-node install of Column Store where you have the data partitioned across multiple nodes. That Docker Compose even includes some sample application data based on a bookstore use case, and you can choose to spin up a BI tool, Zeppelin or Jupyter Notebooks, I believe, to browse that data. So in the case of Column Store, it's nice to be able to have that sample application and to be able to have multiple nodes running so you can get the full experience of Column Store. I talked a little bit about Maxscale. This is our proxy server that can sit in front of a MariaDB single node or a complex topology of MariaDB. It can provide things like data obfuscation, protection against SQL injection attacks, intelligent routing for master-slave setups. It also has some management of failover capabilities in master-slave setups and Galera cluster setups. Again, relatively simple to run, plus Docker Compose. If you're not looking to instantiate that single Maxscale and maybe manually configure it to point to an existing MariaDB cluster, we have a Docker Compose script that can set up a 3-node master-slave setup for you. Lastly, MariaDB, when you put all of these elements together, you can run MariaDB platform in a configuration that has both the OLTP storage engine running and the analytics columnar storage engine running, and automatically does the change data capture, saving the data in that columnar format with Maxscale in front to provide intelligent routing. This is relatively complex to set up. We do have a lot of people who are running it and set it up on their own, but if you wanted to just get a taste of how this works really quickly, we do provide an image called the MariaDB platform single node image that all inside of one container configures all of those components. Again, you've got a version of Maxscale that's up and running, you've got OLTP store, you've got column store, and you have the CDC configured in between them. I do like to point out this is for dev and test purposes only. Certainly, if you've determined that you have a need for that full hybrid transactional analytical processing in your production environment, you would be running on more than a single container. And you can do that. You can configure your individual containers to do that on different nodes. But this is a great way to get a taste of and an experience of that HTAP environment, just with a single Docker run command that stands all that up for you. So all of what I showed you there was MariaDB and containers. Kubernetes, the definition of Kubernetes objects, again, those Kubernetes controllers like replica sets and stateful sets, has now really been superseded by the Kubernetes operator, which is in a technical preview right now, which allows you to define MariaDB specific variables, things like the type of cluster topology you want, whether you want master slave or the Galera cluster setup, the number of replica members that you want. Really what an operator is it's a custom controller. So again, controllers are replica sets, stateful sets, jobs. Operators now are, the MariaDB operator that knows all those specifics of our specific application. It's directly integrated into the Kubernetes API, and it allows you to do these arbitrarily complex operations on, arbitrarily complex software that's running underneath the covers. Again, this is the MariaDB specific view of that. Operators come with custom resource definitions, and in our case, we have two. There's MariaDB, which defines those topology setups that I mentioned, and MariaDB size, which allows you to have to define some predefined size configurations, sort of the t-shirt size approach of small, medium, and large nodes if you want. Again, the Kubernetes operator works a lot like a controller, where you have this definition, this custom resource definition, and you have a control loop that is watching that custom resource definition and making sure that what's been deployed down on those compute resources on the nodes is a match with what you defined in your custom resource definition. Just to look at some of the things that you can define inside those custom resource definitions. Again, cluster topology, that's that choice between single node or master-slave setup or MariaDB Galera cluster setup. Storage size decisions, setting of passwords, setting of number of replicas, etc. Just a quick note on the status here. Fully tested on Google Compute Engine, on AWS. We work very closely with our partner Diamante for those folks who are deploying Kubernetes inside their own data centers. Minikube is a very popular single node installation of the whole Kubernetes environment. So for example, when I'm showing Kubernetes on my laptop, I'm running Minikube. We're also tightly partnered with Red Hat, and it has been certified in OpenShift and is available through the official OpenShift repositories. That link there shows the documentation for the Kubernetes operator that lives inside our knowledge base. And an example of the kinds of setups that you can do. Of course, you can scale the number of nodes. It's not simply only 2 Maxscales and 1 master, but you can have n number of 2 Maxscales, 1 master, and 2 slaves. You can have n number of slaves in these setups. So this is the way forward for us in terms of managing in Kubernetes environments, and we would love to get some feedback on folks' experiences with the operator. Before we go to Q&A, I really just wanted to point you to a couple of resources. Again, there's that knowledge base link that is really the starting point for all things Kubernetes and containers. And then rather than point you to specific white papers and webinars, I think MariaDB.com/resources allows you to search on white papers, webinars, data sheets, all those kinds of things. And if you get stuck and can't find what you want there, or if you just have any kind of question, don't hesitate to reach out to MariaDB.com/contact. And really, no question is too small through that route. It will be routed to the right person, whether it's somebody in technical marketing like me or somebody in the support organization. That really is the way to reach out and get additional information direct from MariaDB on some of the things we've talked about today. So that said, let's jump into the Q&A. There is a mechanism for submitting your questions, and if you'll go ahead and drop those in there, I'll see if I can answer a few of them as they come. So the first question I had is, will this presentation be available as a recording to view later? And the short answer to that is yes. That will be sent out to everyone. I had a question on, are you always downloading a remote image from Docker Hub via a Docker file, or can you bypass the Docker file and download the image directly? So the short answer to that is yes, you can download the image directly. Your Docker environment maintains its own list of images that it has locally. So there are multiple ways you could get that image onto your Docker environment locally. One of them is to clone the GitHub and build the image manually yourself. The other one is if once you've done one download of that image, provided it hasn't changed in Docker Hub or wherever your image repository is located, then it will obviously use that local version of the image as opposed to re-downloading it from the repository. Is the Docker image for MariaDB for Minikube different? The short answer to that is no. And again, that's the great strength of this. We're not producing different images for different instantiations of Kubernetes or containers environments. So I did have a question here that said, is this solution recommended for production environments? And we do have people running MariaDB on containers in production environments. I think the important thing to understand is that the operator is in tech preview, and the way to think about the image files and even the compose files that are spinning up topologies. We also have Docker Helm charts that you can find your way to through that documentation. You want to think of those as templates, that you're going to take those and you're going to customize them a little bit for your particular production environment. So we do want to get to the point where Kubernetes is the mechanism and a production ready mechanism. We're just not quite there yet. But that said, I don't think you need to be afraid of running MariaDB on containers in production environments. It just means that you're going to have some customization that you do in probably in your Docker Compose files or in your Helm chart definitions to lay down those environments. Does MariaDB have its own hub where we can pull images? The short answer to that is no. We've staged our official images into Docker Hub, and there are official images in the official OpenShift repository. Don't think we have plans to host our own repository, but that might be something that would change in the future. And one thing I would say is, again, especially in Docker Hub, you do want to make sure that you're downloading our official images. There are other ones out there that are called MariaDB. Look at the link inside the presentation to know that you're going to the MariaDB Corporation managed Docker images. How does MariaDB internally manage failure on containers? So if you are running in a master-slave setup or in a Galera cluster setup with Maxscale sitting in front, then you get the very fast failover time of, boy, I lost my master node, and Maxscale will manage the promotion of one of the existing secondary nodes to the new master, and it will do a redefinition of, to make sure that all of the incoming connections are directed to that new master, or all the connections that are doing writes. So that the failover capabilities of the standard failover capabilities of either MariaDB and Galera cluster or MariaDB in a master slave setup don't really change. What you do get is behind the scenes is that Kubernetes is going to notice that the node has failed and spin it up and have it join in as the new secondary, so you don't lose your extra read capacity. This allows us to do a very fast failover and takes advantage of the failover logic that's built into Maxscale. Okay, that's it for the questions. If there's something I didn't get to, we'll try and answer it offline. And as we mentioned, the slides and recording will be available. So thank you very much for joining today, and I hope this was helpful.
Great. And with that, Thomas, I'd like to thank you for a great presentation today. I'd also like to thank today's sponsor, MariaDB, for hosting this webinar. And lastly, thanking everyone who attended today. We hope you learned something new that'll help you in your developer career. Have a great day, and we'll see you next time.